Hi all, welcome to another video of Compressible Fluid Flow video lecture series. In the last video, we have completed the derivation of all the rate equations by considering the control volume approach. Now, before going to an important topic which is called wave theory in the case of compressible fluid flow, we need to know about some concepts like bulk modulus of elasticity and compressibility factor. So, first, we will learn about bulk modulus of elasticity. What is bulk modulus of elasticity? We are all familiar with this term because since we have studied this term in way back in our third semester in the subject called mechanics of solids. The denotation is same as before, capital K, and in the case of a fluid, an expression can be given for the bulk modulus of elasticity, which is equal to increase in pressure divided by relative change in volume. Now, this expression can be well explained with the help of a diagram. So, let us go to the open board. We will consider a cylinder piston arrangement. So, we will draw a cylinder. This is a side view of a cylinder. Okay. And a piston is inside the cylinder which can move to and fro inside the cylinder volume. Okay. So, this is that piston. Okay. Now, there is a volume confined between this piston and the cylinder, and this is the initial volume before the motion of the piston. Just consider this volume as initial volume. Now consider the pressure at this initial condition. The pressure is P and the volume is V. Okay, the pressure before the movement of the piston is small p, and the volume between the cylinder and the piston is small v, which is a specific volume. Now, just consider we are moving the piston from right hand side to left hand side. That means we are compressing the gas which is confined in this volume between the piston and the cylinder. So, by compressing, what all changes will occur? Let us see what all changes will occur. The pressure value will be changed from P to P plus delta P. Pressure value is changed from P to delta P. Now, volume value is changed from V to V minus delta V. Okay, that is these are the changes. Now, let us look into that. Pressure, before the pressure was small p before the compression. After compression, the pressure value increase and the change in pressure is delta p. It is a positive value because the pressure has increased. And before compression, the volume was V, and after compression, the volume will decrease, and the change in volume is negative, that is minus delta V. These all considerations has to be considered before going to that expression. Now, coming back to the expression, increase in pressure. What is increase in pressure? By looking into this diagram, the increase in pressure is positive delta P. Okay, and relative change in volume. Relative change in volume means it is a ratio of change in volume to the original volume. That is called relative change in volume. So here change in volume is negative delta V and original volume is V. So negative delta V divided by V is the relative change in volume. Now pressure changes to P plus delta P. Corresponding volume change, relative volume changes negative delta V by V. Substituting to this K relation of the K, we will get delta P divided by negative delta V by V. And we are applying limit. By applying limit, delta P tends to 0. This equation will change like this. K is equal to negative V dP by dV. And we know that for the specific volume, we can write an expression like this. It is a reciprocal of density. Why? Because specific volume is volume by mass. We all know that mass by volume is density. Therefore, volume by mass is the reciprocal of the density itself. Now, before applying for small v equal to 1 by rho, we have to differentiate this. Differentiating on both sides, we will get dv. Initially it was 1 by rho, so the differential of 1 by rho is d rho minus 1 by rho square. So substituting for v and dv in the bulk modulus of elasticity relation, we will get k is equal to rho into dp by d rho. That minus symbol has got cancelled. Okay, this is a final form. This can be considered as a final form for bulk modulus of elasticity. This relation will be recurring throughout in our compressible fluid flow analysis. So k is equal to rho into dp by d rho. Also, this equation is otherwise represented like this: dp by d rho is equal to k by rho. That form is used throughout. When velocity of sound is considered, we can change that equation by using this expression. Okay, that will be coming later. Now dp by dv or dp by d rho for gases and vapors depends upon the process. Okay, in the case of gases and vapor, we can consider different processes like isothermal process, adiabatic process. Okay, so this two values dp by dv and dp by d rho, these values will change according to the type of the process. Now we will consider the isothermal process first, and we will find the isothermal bulk modulus kT. Now we will find a relation for that. For an ideal gas in an isothermal process, we know that the relation is PV equal to constant. P into specific velocity, pressure into specific volume equal to constant. Therefore, differentiating, you will get P dV plus V dP equal to 0. From this we can find P by V, or we can find dP by dV. So the relation will be like this: minus dP by dV equal to P by V. Now from the equations we know that minus V here we have previously derived like this in the previous slide. Minus V into dP by dV is K. Okay, so if you are taking this V to the left hand side, it will be minus V into dP by dV, which is equal to K. That means K is equal to P, and this K is in the case of isothermal process, so we will give a suffix T for that K. Therefore KT will be equal to P in the case of an isothermal process. That means bulk modulus of elasticity for the case of isothermal process will be equal to pressure, okay, for an ideal gas. That also has to be considered. Okay, now adiabatic bulk modulus, K suffix S. Let us find a relation just like in the case of isothermal flow. For an ideal gas in reversible adiabatic process, our relation is PV raised to gamma equal to constant, where gamma is the adiabatic index. Here also V, small v is a specific volume, P is the pressure. Now differentiating on both sides, we will get P into gamma into V raised to gamma minus 1 dV plus V raised to gamma into dP equal to 0. From this we will find minus dP by dV again, and it will obtain like this: gamma P by V. Okay. Here also we will find the bulk modulus of elasticity term, which is got by taking this V to the left hand side, which will change this equation into negative V into dP by dV, which is nothing but bulk modulus of elasticity. But in this case, it is adiabatic bulk modulus. Therefore, from the equations we will get Ks is equal to gamma P. K is equal to gamma P. Okay, that means in the adiabatic flow, in the adiabatic process, our bulk modulus of elasticity will be equal to the product of adiabatic index and pressure. Okay, so we can also write, we all know that P is equal to KT in the case of isothermal flow. Therefore, Ks and KT, adiabatic flow bulk modulus and isothermal flow bulk modulus can be related like this: Ks is equal to gamma into KT. Okay. This relation is very important. It has been asked in so many university question papers, so it is important to learn this relation. Now coefficient of compressibility, that is this was the end of the bulk modulus of elasticity. Now what is coefficient of compressibility? The name itself seems very important because compressibility, we are learning about compressible fluid flow. So we all know what is the importance of the compressibility. So coefficient of compressibility, it is denoted by beta, and for a fluid it is defined as relative change in volume divided by change in pressure. This is too familiar, right? Because it is a reciprocal of the bulk modulus of elasticity itself. Okay, that means beta is equal to 1 by k. Now applying the relation for k from the diagram which we have drawn earlier, we can, from that diagram we can give the change in pressure and relative change in volume, etc. And after applying the limits, we will get the relation 1 by v, negative 1 by v dv by dp, which is nothing but the reciprocal of bulk modulus of elasticity. Now substituting for dv, which is 1 by rho, and we have also substituted for dv and v also. Therefore beta is equal to 1 by rho d rho by dp, which is nothing but 1 by k. Comparing the equation, we know that k is equal to 1 by beta, or beta equal to 1 by k. So these two terms, which is bulk modulus of elasticity and coefficient of compressibility, and also bulk modulus of elasticity for two different processes, and finally the relation between k and beta, which are bulk modulus of elasticity and coefficient of compressibility. All these are very important. These things have been asked in so much previous exams. Now for ideal gases, isothermal coefficient of compressibility, we are finding the coefficient of compressibility in the case of isothermal process and also for the adiabatic process. So beta t is basically 1 by kt, therefore it is 1 by p. Now isentropic coefficient of the compressibility, it is for the adiabatic process, beta s suffix s is equal to 1 by k suffix s is equal to 1 by gamma p, which is nothing but the reciprocal. Therefore beta t is equal to gamma bs. We can get this expression from the above two relations. Beta t is equal to gamma bs. Gamma is the adiabatic index. Now as a statement, consider this. For the liquids, the difference between the coefficient of compressibility for isothermal and adiabatic process is negligibly small. That means this beta value for isothermal and adiabatic process is very similar. Their difference is very small because they will be approximately considered to be same in the case of liquids which are incompressible. So only in the case of compressible fluids, those values will differ. Okay, will differ in the difference will be very large. So next we will be starting wave theory, and then we will start that concept in the next class. So we are all set to start an important topic called wave theory, and that will be covered in the next video. Thank you.